Hey everyone, and welcome back as we continue on with lesson 3.2 covering the least squared regression line. And today is going to be part 2 of our 3-part video series. So in the previous video, we learned how to make predictions using a regression line. We talked about the concept of extrapolation and why it occurs. We learned how to calculate and interpret a residual. We learned how to interpret the slope and y-intercept of a regression line, and we were able to determine the equation of the least squares regression line using technology. What we're going to be doing today is continuing on with that. We're going to learn about the computer output variation of that as well. We are going to construct and interpret residual plots, and we are going to interpret the standard deviation of the residuals and r squared and use these values to assess how well a least squared regression line model fits our relationship. So remember again that a regression line is just simply a prediction line. It helps us predict any outcome value for any given income value. And our equation looks like this. It comes in the form y hat equals a plus bx, where y hat is the predicted outcome, a is the y-intercept, which is the predicted outcome when x is equal to 0. B is the slope, which is how much y hat changes for every 1 unit of x. And x is just any arbitrary value for the explanatory variable. And so as we continue on here, what the least squares regression line is, and we will abbreviate this as LSRL, least squares regression line. This is also known as the line of best fit. By definition, the least squares regression line is the line that makes the sum of the squared residuals as small as possible. In other words, it minimizes the overall margin of error. So as a quick visual as to what this looks like, you can see that we have a link here. Click here to see the least squared regression line in action. So basically the way that it works is we've got these 5 data points, and if we were to show just an arbitrary regression line, we can see that this blue line does a good job of representing these 5 data points. It's a positive slope, it splits the difference, all of those are good. Right? Now, by clicking this next box, it shows the squares associated with the residuals. So we can see that for each of those purple dots, how far away it is vertically or horizontally from our regression line, and then a square is made. Now, the larger that square is, or each individual square is, the larger the error for that one value. And then if we were to take the sum of the areas of all of those squares, obviously the larger the sum of the squares, the worse off my data is. The bigger the square, the worse off that one value is. The larger the sum of the squares, the worse off all values are. So if I were to show this red line, which you can see over at the left-hand side, it says y equals 15. That means the sum of the area of those squares is 15. So what a least squares regression line does is it minimizes the size or the sum of all squares. And so you'll see I've got some black sliders on the bottom right. If I were to increase the slope, okay, this blue line obviously has a positive slope, but we see that it doesn't split through the points. So it creates very large errors. And as I decrease this, we see that it makes some of the errors bigger, some of the errors smaller. Okay, so as I just kind of manipulate with that a little bit, looks like right around 14.8 is the lowest I can get if I do this. And that's just manipulating the slope. I haven't even touched the y-intercept yet. So now if I manipulate the y-intercept a little bit, I can see that again, some of the individual boxes increase, some decrease. And so really, if I just keep playing around with this, I can look at that red line and what that height is, and I want to just try to minimize whatever that value is. So here I'm at in the 10 range, and I could keep manipulating as much as I want, but ultimately I'll never get to 0 and that's because these points are not in a straight line, so I'll never get to a point where there's no error whatsoever. But a least squares regression line is going to take every possible blue line that you just saw me make, plus the ones that I didn't make, and it's going to determine which one produces the lowest set of errors, the lowest sum of the areas of those errors. And so if I click this last box here, we can see that my blue line was actually pretty close here. That orange line that's dotted is the actual least squares regression line. So if I kind of remove some of this other stuff, that orange line is the line of best fit, or it is the least squares regression line for this data. Okay, so example 4a, or example 4, is basically just going to be a review of the concepts from yesterday. So the table below shows the number of people at a party and the total amount the total bill amount for their dinner. So at this time, I'll ask that the video get paused. You put this data into, again, list 1 for people and list 2 over here for the bill amount, and we'll resume the video when you are done. Okay. So part A, calculate the equation of the least squares regression line defining any variables used. So I've got my data here in list 1. Oh, I gotta love when those ads come through. All right, so I've got my data here in list 1. So to calculate my least squares regression line, stat, go over to the calc tab, and option 8 is our linear regression, a plus bx. Press enter. Make sure, again, my x list is list 1, my y list is list 2. And I can see that y equals a plus bx is the general form. Over on the right, a is equal to 16.5, b is equal to 8.5, and then we have r squared and r. So pretty strong correlation here at about 0.87. So 16.5 and 8.5 are two values. So again, y hat equals 16.5 plus 8.5 x. Just taking those numbers from the calculator. Y hat equals a plus bx. But I want to define my variable. So instead of y hat, I have to think about what y represented, and that was the bill amount. So the predicted with the hat bill amount is equal to 16.5 plus 8.5, and then our x was people. Okay. So here is the equation of the least squares regression line. This is the line of best fit. That's all your calculator will give you. It won't give you a line that's not the best fit. So interpret the slope and the y-intercept. So remember that our slope is how much does y change for every 1 unit of x. Okay, so as far as the slope goes, we would say that the predicted bill amount, and because our slope is positive 8.5, it's going to increase. The predicted bill amount increases by how much? $8.50 for every one person. As a new person comes to the table, the total bill amount increases by about $8.50. And then when it comes to our y-intercept, remember that the y-intercept is simply what is the predicted outcome for when x is equal to 0. So we would say the predicted bill amount for 0 people is $16.50. $16.50. So this is to say that if there's nobody at the table, it costs $16.50, which again, we know is not true. But in the last video lesson, we discussed how the y-intercept isn't always going to make sense in context. And that's often because your y-intercept is usually an extrapolated value. Yep. Next, you and 7 others will be going out for dinner to this restaurant. How much would you expect the bill to be? So you and 7 others means that we have 8 guests. So if the projected bill amount is equal to $16.50 plus $8.50 times the number of people, we just simply take that 8, drop it in there. The projected bill is 16.5 plus 8.5 times 8. And we can see that we get $84.50. So now we write our sentence. We would expect to pay $84.50 for a party of 8 people. Okay. Lastly, calculate and interpret the R value between party size and cost of the bill. So this just goes back to our calculator steps from before, and in fact, we already have it calculated from earlier on. We can see that our R value, or the correlation coefficient, is 0.87. So as a quick review of correlation, remember that it's a value from -1 to +1. The larger the absolute value is, the stronger the relationship. Positive just means that the direction is positive. Negative means that the direction is negative. As x goes up, y goes down. The closer the absolute value of R is to 0, the weaker the relationship is. So in this case here, we have an absolute value of almost 0.9, which when 1 is the greatest, we're pretty high up there. And then again, this is a positive value, 0.87. So we would say something like, there is a strong positive relationship between party size and the cost of the bill. Typically, the larger the party, the greater the bill. So remember that when we interpret an R value, we discuss its strength and direction, and then if it is strong or moderately strong, we include that context of typically as x goes up, y goes up, or as x goes up, y goes down, depending the direction, with context. Okay. So that's all good review there. Now, what's new is going to be something called a residual plot. So a residual plot is a scatter plot that displays the residuals on the vertical axis and the explanatory variable on the horizontal axis. So here's basically what we're doing. If I were to go back to the calculator really quickly, and I were to have a scatter plot of my data, I'm going to take it one step further. The equation for the line of best fit we said was 16.5 plus 8.5x. Okay. So we can see how our line of best fit cuts through those points on the scatter plot. Now remember what we talked about in the last video, where residuals are the vertical segments connecting the line of best fit to each of those individual values. What a residual plot does is it essentially takes our slanted least squares regression line and it rotates it such that the least squares regression line is perfectly horizontal. Then what you'd want to think about is like if the residuals, those vertical segments, were strings and the values above the least squares regression line were helium balloons and the points below the least squares regression lines were rocks. If we were to rotate our least squares regression line, the helium balloons would stay above, but they'd be fixed at a certain length based on how long the string or the residual is. Likewise, the rocks would continue to hang below the least squares regression line, but at a fixed length of whatever the string was, which is, again, represented by the residual. Okay, so all we're doing is we're rotating this diagonal least squared regression line downward such that it's a flat horizontal line. And so you can kind of see that idea here. This bluish grayish line going through is the least squares regression line, but it's been rotated such that it's horizontal. Same thing here, same thing here. And so here's the general idea. A residual plot, and we want to make sure we know these rules. A residual plot without any pattern indicates that a linear model is appropriate. If there's no pattern, what that means is your least squares regression line cuts nicely through your scatter plot such that you have roughly an equal number of points above and below at an equal distance away. But if we have a pattern, a residual plot with a pattern is going to indicate some type of linear relationship is, or a non-linear relationship is appropriate. Okay, so what that might be would be something like this. If I have a scatter plot that looks like this, well, my least squares regression line is going to look like this. And if I were to rotate this down and this up such that it's horizontal, what that would look like is something like this. Okay, that's essentially what we'd be looking at. And we can see this curved pattern here in the residual plot, which means a non-linear model is best. So, to answer some basic questions, for each example below, determine whether or not a linear model is appropriate. Well, when I look at this one here, I can see that there's really no pattern in the data, right? We're pretty evenly distributed above and below. So yeah, a linear model is appropriate for this. However, here, I can see that curved pattern. So, no, a linear relationship is not appropriate. And we comment on that. Because of the curved pattern, of the residuals, a linear model is not appropriate. Now, a residual plot doesn't tell you what type is. It just is a yes or no for linear. Yes, this is linear. No, it's not linear. Excuse me. Okay, so now when we look at this one, this is one that usually students will debate on. Yes, there's a pattern. No, there's not. What we can see is that we're pretty evenly distributed. We have points both above and below throughout. Okay, but what we see is that early on in the process, the residuals are small. And as x gets larger, the residuals start to increase even more. Okay? So although it's not a curved pattern, there's still a pattern taking place here. And so what we would say is, no, a linear model is not appropriate because as x gets bigger, our errors increase. As x gets bigger, our guesses become less and less accurate. So that means a linear model isn't going to be very helpful for us here because we're not increasing by roughly the same amount. We don't have common residuals like we have here throughout. So, no. Because residuals increase more and more as x increases, a linear model is not appropriate. So this is kind of counterintuitive. We like patterns. Naturally, our brains gravitate towards that. But in this case, if we see a pattern, that means a linear model is not appropriate. When we see no pattern, a linear model is appropriate. So we want to make sure we know those rules. As far as making a residual plot on your calculator, you have the ability to do this. So step one, you can see you're going to enter your data into list 1 and list 2, which we've already done. You have to calculate your least squares regression line. The most common error that gets made why students can't do this on their calculator is because they don't calculate the least squares regression line. Remember that a residual plot is taking the least squared regression line and it's rotating it. If there's no least squares regression line to rotate, your calculator can't make the graph. So you have to calculate the least squared regression line. Then once you do that, you hit your second y equals to go to your stat plots. You choose the scatter plot option, and your x list is going to be list 1, but your y list is going to be resid, which stands for residuals. And the way that you find residual or resid is you're going to go, and I'll just second y equals. You can see that I chose the scatter plot option, but for my y list, I'm going to hit second stat, and then you can see my option number 7. So how did I get there again? Second stat button, resid, and of course I got to redo all this, so I apologize. There on second stat, option 7 is resid, zoom 9, and I got to get rid of this. So there is my residual plot based on the scatter plot that we had for party size and bill amount. And as we look at that residual plot, we can see that there's no pattern. We have one high residual in the middle, but we don't have like a continuous pattern. Most of our residuals are pretty close to the line. Therefore, a linear model seems to be appropriate. Okay. So that's exactly what question 6 here is asking. Determine if a linear model is appropriate for the data in example 4. Include a sketch to support your answer. Okay, so for a residual plot, we just make our T. This is residuals. We can see that our residuals are basically going from negative 20 on the vertical axis up to a positive 30. can see that our horizontal axis is going up to from 0 up to 10. And then from there, all I would have to do is, again, just make a rough sketch. So I've got something here, 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 there, down here, and a little bit lower, right there. Okay. And then our comment, because there is no pattern in the residuals, a linear model is appropriate. Okay. Residual plots, no pattern, good. Linear works. Pattern, no good. Linear is not appropriate. Okay? Now, what's important to know is this. Okay? It's one thing to know if a linear model is appropriate, which is what a residual plot tells us. Yes, it is, or no, it isn't. But what it doesn't do is it doesn't tell us how well it fits. Okay? So it's another thing to know how well the model fits. How good is this? How accurate is it? Yeah, it's linear, but how linear? How close to being a perfectly straight line is it? Okay? One of the things we know about is correlation, and therefore one of our two options here is related to correlation. We have two ways in order to determine how well a line fits our data. One of them is the standard deviation of the residuals. So what we do is basically we calculate the residual for each of our data values. And then once we know what each of those are, we calculate the standard deviation of those. And what that measures is the typical residual, or approximately how much any given data value is from the predicted value. Okay? Typically, how far off are we from our prediction? If you remember a standard deviation by definition, typically how far are all values away from the mean? Standard deviation of the residuals, typically how far away are all predictions from the actual values. Okay, so that's one way. The other way we can do this is we can calculate what's called the coefficient of determination, which is r squared, which is literally the correlation squared. Now, by definition, r squared measures the percent of variation in the response variable that can be explained by its linear relationship with the explanatory variable. Okay. And whenever you see a question that says interpret r squared, we are using the definition. We're going to say blank percent of the variation in whatever our response variable is, with context, can be explained by its linear relationship with blank, whatever the explanatory variable is in context. Okay? So, as a quick calculation here, using the dinner party data, find the standard deviation of the residuals to determine how much a typical prediction is off by. Okay, so when I go to my calculator, what I'm going to do is edit. List 1 and list 2 are already set with our values. Remember, we've already calculated a least squares regression line. So one of the cool things that we can do is, if I go to list 3, I press enter. Now I've got that blinking cursor on L3. It's asking, what do you want L3 to be? Well, I want L3 to be the residuals. So remember the way we calculate the residuals or find the residuals is we hit second stat, option 7, and you can see that it says L3 equals resid. So now I press enter, and L3 is now filled with all of the residuals. So the residual from point number 1 person, $8.50, is negative 16.5. Okay, so now that we have all of those residuals in list 3, in order to find the standard deviation of the residuals, all of the residuals are in list 3. So I'm going to go stat, calc, one variable stats. Right? One variable stats is where I find my mean, my median, my standard deviation. But I don't want to take it on list 1. I want to take it on where my residuals are located, which are in list 3. Okay, so I can see that the standard deviation of list 3, which is my residuals, the standard deviation of my residuals is 12.62. Okay. So now that we've found the standard deviation, okay, we can put this into context, right? Determine how much a typical prediction is off by. Okay. Typically, a predicted price is off by about $12.62. Okay. So not the greatest, right? $12, I mean, I guess it depends on your party size, right? If you've got a lot of people, being off by $12 on a large bill isn't that great. But on a smaller party where there's only maybe 3 or 4 people, to be off by $12 isn't the best. But remember, it's basically taking all possible values within our data set. Okay, big parties, small parties, everything. Now, the other one it asks us to do is to find R, or find and interpret R squared. So, same thing I would do before to find R. Stat, calc, option 8 from list 1 and list 2. And I can see that my R squared value is given to me. R squared is 0.75. Okay, so that's the find portion of it. Now the interpret portion is taking its definition and putting it into context. Okay? R squared measures the percent of variation in the response variable. So 0.75 is 75%. 75% of the variation in my response variable. Bill amount can be explained by its linear relationship with the explanatory variable. Okay. Now, what does that mean in layman's terms? Right? We know that as the party size increases, the bill amount is going to increase. Well, how much of the bill increasing is accounted for strictly by the number of people? 75% of it. Okay? 75% of the amount that the bill changes is based on how many people there are and how the bill changes. Okay? So what's the other 25%? It could be what the people actually ordered, right? Some people may have ordered a cheaper dish. Some of the people may have ordered a much more expensive dish. Okay, they could have gotten dessert or something like that as an additional thing. So the strong majority of how the total cost changes is based on the number of people that there are, but there's other factors that contribute to the other components of it. Okay, so that's what R squared tells us, is what percent of Y changes because of X changing. Okay, so the larger that number is, the stronger the relationship. Okay, the lower that number is, the less of an impact X is having on Y, therefore the relationship isn't as strong. Okay, and so now the last thing we're going to talk about is how we can get these values from this computer output. And actually, I'm going to change my mind on this. We're going to end this video right here because we can use this as a nice review of the previous lesson and tie it in later on. So we're going to end it right here, just talking about how well our lines fit. Residual plots, how do we make them? When is it appropriate to say linear versus non? And then our measures to say how accurate we are. The standard deviation of the residuals and R squared. Okay. As always, if you do have any questions, please feel free to reach out to me. Otherwise, thank you for watching, and we will wrap up with our final lesson for 3.2 in video lesson part 3. Take care, everybody.